Hi everyone. So in this video I wanted to end this section by giving you a bit of an introduction into how interatomic potentials are used in research. So to briefly recap, what we have been discussing are these interatomic potential curves. These describe the interaction energy between pairs of atoms, separated by some distance r. This is the distance r on the x-axis. And so you can see the potential energy then varies as a function of this distance r. And we have this minimum energy here, which occurs at some distance r naught. And this is our equilibrium separation. So if we have just two atoms forming a diatomic molecule, then this potential energy curve describes the energy of that molecule and tells us how far apart the two atoms will be in our diatomic molecule. And we also then went on to discuss the situation for crystals. So in crystals, we have not just two atoms, we have lots of different atoms. And so we have to then, we pick some atom and we can use our interatomic potential to calculate the potential energy because of its neighbors. And so we have to sum over all of the contributions from all of these different atoms in the crystal, and when we do that, then we can find the cohesive energy of our crystal. And then in this situation, these atoms are already in their equilibrium positions, right? This is a stable crystal. We know, these atoms are in the positions that they like that they like to be, determined by this minimizing this cohesive energy function. But you can see how you can use this if you have a potential energy curve for the atoms that you're interested in, then you can apply it to study situations that you haven't previously looked at. And here is an example where we have a molecule that is going to adsorb onto, or is going to form, this molecule here is going to form a bond with this small crystallite of the material. And we might not know, before we do this study, we might not know exactly what is for example, we might be just interested in calculating the bond length between the molecule and this crystallite after the bond is formed. And so we can pick some configuration of these atoms and we can calculate the energy using our interatomic potential, and we might find that we're somewhere up here. And now we can adjust the positions of the atoms and do the calculation again, and we might find that the energy, we sort of tend to do these, and there are sophisticated ways to do this to make sure that we move towards the minimum. But in the simplest case, you can think about just moving this molecule toward the surface, and then you find that the energy has got lower, and we continue to optimize the positions of the atoms until we get down to a minimum energy configuration, and that tells us then how this molecule in this case likes to bond to this small crystallite. And so in fact, I used such a interatomic potential for my first ever research paper. And this is a research that I did as a fourth year undergraduate. And I wrote the paper in my first year of my PhD, but the research I did in my fourth year project. And I was interested in calculating the energetics of steps on the silicon 001 surface. So I think we already described these two diagrams in our previous discussion of, in lectures we talked about, I gave an example where we went through the scanning tunneling microscope, and I described the fact that the surface reconstructs into these rows of paired silicon atoms. And so we had an interatomic potential that worked well for both the describing the properties of the bulk crystal and also describing the properties of the reconstructed surface. And then what we wanted to do is to try and use the same interatomic potential to calculate the energetics of these atomic height steps on the silicon surface. So which type of step, there are different types of steps, and which types of those are more energetically favorable than others was essentially the question that we were interested in answering. And here's a more modern example. So here, this is just an example that I found online. And they're now using interatomic potential to study the properties of these core shell nanoparticles. So the nanoparticle consists of a core of iron and an outer shell of gold. and in this case, they've used two different types of forms of interatomic potential, and if we start with this crystallite, sort of artificial looking crystallite, and then we allow the positions of the atoms to optimize, then the one potential is giving this result over here, which may not agree with the experiment, and then a better version of the potential is maybe producing these core shell nanoparticles in better agreement with the experiment, right? Because the interatomic potentials are, in the end, they're only approximate. So perhaps a better way to do a study like this would be to solve the Schrödinger equation, as we've talked about. So you can give the Schrödinger equation the positions of all of these nuclei. We can solve the Schrödinger equation to get the distributions of the electrons around the positively charged cores, and then we can optimize using a similar procedure as So you calculate the forces because of the negative electron charge and the positively charged ion cores, and we optimize. The problem with trying to do to try and address this research problem with the Schrödinger equation is the size of the problem. So there's lots of atoms involved in these core shell clusters, and you can see that they're also optimizing this at finite temperatures, which introduces additional complications. And it's just not practical to solve we have numerical methods for solving the Schrödinger equation, but they're very computationally expensive, and it's not practical for when you get to these large systems. And so it's very common to use interatomic potentials for a research problem like this. And then maybe just one final note to say that the real interatomic potentials that are used tend to be a lot more complicated than the simple pair potentials that we've talked about in this module. So they might for example, you could consider the angle. If you consider three neighboring atoms, you could consider the angle that's formed by those three atoms. And there could be a term in your interatomic potential that also accounts for these angular variations and things like that, just to give you a brief idea. But I don't want to talk too much about that because that's beyond the scope of the module. And all I'm really trying to do here is to give you an idea that these interatomic potentials really are used in modern research, and they are indeed very useful.